Hi, this is Preston Culbertson. This is Lab 7 at Home, which is about elliptical orbit. And my objective this week was using position data given to me by my instructor to determine the mass of a black hole being orbited by a star. And my results were that by calculating dp/dt, I can use the momentum principle to calculate the mass of the black hole. I can also decompose that net force into its parallel and perpendicular components to better understand the star's orbit. So first I'm going to explain the physics behind this problem, and the first thing that we do is we pick a system and a surroundings for this problem. Our system is the star that is orbiting the black hole that we've been given the position data for, and my surroundings is the black hole that's acting on the star, and the black hole is the only force acting on the star through gravity. So we're going to use the momentum principle to calculate the net force on the star, and how we do that is we calculate the change in momentum over the change in time. So in Python, we set up a couple initial conditions, including our delta t, which is 1 day in seconds. And then using the position data given to me, I actually iterated through each step of that, and I calculated by using delta r over delta t equals v. I calculated the change in position over the change in time for each time step, which gave me, I stored those in two arrays of called xvel and yvel, which were arrays of velocity data. And so that each time step I picked a v initial and a v final, and then I multiplied both of those times the star's mass to get a p initial and a p final. And so then from that I could calculate a delta p, which is p final minus p initial, and when you divide that by the delta t, you get dp/dt, which is equal to F net through the momentum principle. Then using Newton's law of gravitation, I could calculate the mass of the star. The F net is only, it's equal to the magnitude of Fg, since gravity is the only thing acting on the star. And so then we get Fg through Newton's first law of gravitation. We get that Fg equals g, gravitational constant, times the mass of the star, times the mass of the black hole, divided by the distance between them squared. And so then we calculate r is the difference between the position of the star and the black hole. And then we rearrange the terms of the equation to give us that the mass of the black hole equals F net times the distance squared over g m star, which gives us 3.75 E31. So now I'm going to show you my model that I created by plugging the mass of the black hole that we solved for here into a iterative calculation, which calculates how the star moves around the black hole by calculating the force of gravity on it at each point. And so when I run it and plot it against the position data, which is given in red, my model is given in black, we see that it's a little bit inaccurate. And the reason for that is that I calculated using only one time step what the mass of the black hole is. And so that means that actually it's going to give a different value here than here, because dp/dt isn't necessarily equal to F net when dt isn't infinitely small. And so when I adjusted the parameter of the black hole's mass to fit the end data a little bit better, we see that the model matches the position data a lot better. So now I'm going to go to the what does it mean question, which is how can we decompose dp/dt into its parallel and perpendicular components as related to the momentum? And that's something that's really useful to do when analyzing curving motion. And so what we do is from the chain rule, we get that to break it down, it's the magnitude of p dt times p hat plus dp hat dt times the magnitude of p, which gives us respectively the perpendicular and parallel components of motion. And so in VPython, what I did is I calculated the parallel component of motion by using this formula. And then I subtracted that from the F net to give me the dp/dt perpendicular. And so now I'm going to show you the model where I plotted those. And you can see this blue arrow represents the dp/dt parallel, and this red arrow represents dp/dt perpendicular, whereas the black arrow represents the force, the F net. And so the rest of the what does it mean question is how is dp/dt different from F net? And so it's different because dp/dt comes from experimental data, which is the change in momentum over the change in time, whereas F net is just a concept. It's a mathematical derivative of the momentum function over time. And so when dp/dt, or when dt is infinitely small, when we actually take a derivative of p function, we get dp/dt equals F net. So now I'm going to go to the what if question, which is what if we replace the black hole with another black hole at the same location and the star's motion remain unchanged? could that black hole have a different mass than the original? And so we know that the only force acting on the star is the force of gravity, which is directly proportional to both the mass of the star and the mass of the black hole. And we also know that since motion remained unchanged, r old equals r new. And since F net is the second derivative times the scalar of r, we know that F net old equals F net new. And so then when we look at these equations, we see that G remains the same between both, M remains the same between both, and R, again, the positions remain the same, so R remains the same between both. So since all the others are constants, we know that the mass of the black hole new equals the mass of the black hole old, and thus the mass of the black hole must be the same between both.
So that's all I've got. Thanks for watching. If you have any questions, leave them in the comments below. Thanks.